Dear students, welcome to this lecture on the observability of discrete dynamical systems. So, in this lecture we will see the definition of observability and some conditions on the observability of discrete systems. So, this is analogous to the continuous systems, the observability and the condition of observability of continuous systems. Only thing is there will be little changes for so as to deal with the discreteness of the system here. So, the procedure will be almost same like a continuous system with a little small changes. So, let us consider the discrete control system given by equation 1, that is x of k plus 1 equal to a of k x of k plus b of k u of k. So, A is n cross n matrix, A of k is n cross n and B of k is n cross m matrix, and x of k is the state variable and u of k is the control variable in the spaces. X of k belongs to Rn and u of k belongs to Rm for each value of k. K is ranging from k0, k0 plus 1 etc., k0 plus n. So, these are the time instances in which we consider the dynamical system, and the observation of this system is y of k equal to Ck x of k. So, now the definition of observability is similar to that of the continuous system except the discreteness of the system. So, the system given by 1 and 2 is said to be observable if the knowledge of the control u of k for these instances k0, k0 plus 1 up to k0 plus n minus 1 and the knowledge of the observation y of k which is for k equal to k0 up to the last stage k0 plus n. So, this knowledge is sufficient to obtain the state of the system x of k for all values of k uniquely. So, instead of saying that x of k should be known uniquely for all instances, we can also say that the observability means if the initial state x of k0 is obtained uniquely from the knowledge of u of k and y of k, then also the system is observable, because we can see that the solution of the equation 1 is written as x of k equal to phi of k k naught into x naught plus the summation as given here in the equation 3, where we have seen in the previous lecture that phi of k k naught in the general case of the time varying system, it is a of k minus 1, a of k minus 2 etc., the products a of k0. So, with this notation we write the solution 3 of the dynamic control system 1. So, if we know x naught, that is x of k0 equal to x naught uniquely, then from equation 3 we can get x of k for all values of k, that is k ranging from k naught to k naught plus n. So, that is the observability of the system, the definition of observability of the system. Now, we will see from equation 2 y of k equal to c of k into x of k, where x of k is given by this expression. So, if you multiply equation 3 both sides with c of k, we get the equation 4, that is the observation in terms of this summation, and taking this summation term to the left hand side, we will get y of k minus the summation equal to c of k phi of k k0 into x0. So, this is for k equal to k0 plus 1 etc., k0 plus n. Now we can write, give the notation y bar of k for the left hand side of the equation 4, because all these quantities are known to us. Y of k is the observation, u of k is the control, and for all the instances the matrices B, C all are known to us. So, we can say that the left hand side is known and we denote it by y bar of k for these instances, k equal to k0 plus 1 etc., k0 plus n. So, from that equation we get y bar of k equal to C of k phi of k k0 x0 from the previous slide. So, multiply both sides by this matrix, that is phi transpose k k0 into C transpose k, and then using the summation from k0 plus 1 to k0 plus n, we get this equation 5 here, okay, multiplying by this matrix and then using the summation both sides we get this expression. Here x naught is a constant vector, so we can write it outside the summation as given in the equation 5. Now let us call this square bracket summation as the matrix M. So let M be summation k ranging from k0 plus 1 to k0 plus n of phi dashed c dashed c into phi of k k0, this matrix. So we can note that the size of the matrix, it is a square matrix, it is a n cross n matrix, because A is a n cross n matrix. So the state transition matrix is n cross n, and the product will give finally a n cross n matrix, and it is a symmetric matrix because we can see that phi dashed c dashed is one matrix and its transpose. So they are multiplied and we are taking the summation over a symmetric matrix. So we get M as a symmetric matrix here. The above n cross n symmetric matrix is called the observability Gramian matrix, the matrix M, and we can write from the equation. If you denote the equation 5, the left hand side, if you denote it by a vector v, then we can write the equation 5 as m into x naught is equal to the vector v. So this can be done for all systems with irrespective of what the matrix A, B, C etc. Of the dynamical system, but the system will be observable in the time instances k0, k0 plus 1 etc., if and only if the observability Gramian matrix M is non-singular. So for observability we need the condition that the matrix M is non-singular. So this is exactly similar to the continuous case. In the continuous case, what we have earlier seen is if the initial time is t0 and the final time is capital T, then the observability Gramian for the continuous case is given by phi dashed t t0 into c dashed of t into c of t into phi of t t0 dt. So this matrix is M matrix for observability Gramian matrix for the continuous case. So if M is non-singular, then the system is observable for the continuous case. Now for the discrete case we have a similar result and we can prove it in a similar fashion. So now let us see the sufficiency of the condition. If M is non-singular, it is invertible. So directly we can see from equation 6 we will get x naught uniquely. The initial condition x naught is obtained uniquely by taking the inverse. M inverse V is x naught. So So, according to the definition of observability, if the initial condition is obtained uniquely, then we call the system observable. So, sufficient condition is proved directly like this one. Now, the necessary condition, if the system is observable, then we have to show that the matrix M is non-singular. So, let us assume that M is singular. So, in that case there will be a vector beta in the space Rn and beta is non-zero such that M into beta is equal to 0 because M is singular. So, then we will get beta transpose M into beta is also equal to 0 from that expression. So, that implies if you substitute the value of the matrix M, we will get summation k equal to k0 plus 1 to k0 plus n. The definition of M as we have seen here this expression. So, we multiply in the left with beta dashed and in the right with beta. So, we get this expression summation k0 plus 1 to k0 plus n beta dashed phi dash c dashed c phi into beta equal to 0. Now, we observe that these three terms beta dashed phi dash c dashed and c phi beta. So, these are transposed to each other. So, it means that this vector, it is a row vector, it is a column vector and the product will give the norm of this vector. So, norm square of c of k phi of k k0 into beta norm square summation is equal to 0 and inside the summation all the terms are positive, therefore, each term separately should be equal to 0. So, we get c of k phi of k k0 into the vector b beta is equal to 0 for all values of k from k0, k0 plus 1 etc. up to the last stage. So, now the system observability definition is using the knowledge of the control u of k and the observation y of k. If you are able to get the initial condition uniquely, then the system is observable. So, let us assume that the control u of k is 0 for all k. So, for using the observability definition, let us say u of k is 0 for all k and the initial condition x naught is c times beta, where c is any constant, because we know that beta is non-zero according to the assumption here we assume that M is singular, therefore, there exists a non-zero beta. So, beta is given to us and we assume that initial condition x naught is c times beta for some value of c. Then from this last equation 7 we will get that c of k phi of k k0 into c times beta is also equal to 0 for all value of k. So, this implies that if x naught is 0, that is if x naught is 0, then c of k phi of k k0 into 0 is 0 and for non-zero value of beta that is also 0. So, for various initial condition we get the same observation, this y of k equal to c of k phi of k k0 into x naught. Because u is 0 we get the observation y to be like this, and for let us say two different initial condition 0 and beta we get the same value y of this is identically equal to 0 for all values of k. So, this is a contradiction because the initial condition should be obtained uniquely for a given observation. So, that is violated here. So, it means that the beta cannot be non-zero, it has to be 0 if the system is observable. So, based on that we say that the matrix M has to be non-singular, otherwise we will get a contradiction. So, this proves the result that the necessary and sufficient condition for the control observability of the system 1 and 2. So, now we will see a simple example to illustrate the observability. So, consider the system x1 of k plus 1 equal to minus x1 of k plus k times x2 of k, here x1, and x2 of k plus 1 equal to 2 times x of k plus u of k. Here u of k is the control variable and x1, x2 are the state variable. X of k is x1 of k, x2 of k belongs to R2. R2 is the state space and u of k is a single function. So, it belongs to R for each value of k. So, the control space is R, state space is R2 here, and the observation y of k is given by x1 of k minus x2 of k. This gives the observation for the values k equal to 0, 1, 2, 3 up to the last instance k suffix n. Now, to test the control observability of the system, we can utilize the observability Gramian matrix. So, let us take the simple case where the final instant is 2, initial time is 0 and final time is 2. So, for this we test the observability of the system. So, here in this case A of k is given by minus 1 k 0 2 and B matrix is 0 1, C matrix is 1 minus 1, and so the state transition matrices phi 1 comma 0 and phi 2 comma 0 to be obtained, because for the M matrix we need the formula that k ranges from k 0. So, if you see the M matrix here, k varies from k 0 plus 1 to k 0 plus n, k 0 plus n of phi k comma k 0 dashed and c dashed of k into c of k phi of k k 0. So, this we have to calculate. So, in this case k 0 is 0 and n is 2. So, we have to find from 1 to 2 here, that is k starting from 1 and 2, there are only 2 terms we have to calculate. So, we have to obtain these terms. Here when we put k equal to 1 and k 0 equal to 0, we will get first term is phi of 1 comma 0, that is phi dash, that is a of 0, that is phi of 1 0 according to the definition of phi k k 0 is a of k minus 1, a of k minus 2 etc. a of k 0. So, in this case k is 1 and k 0 is 0. So, we will get only a of 0, that is the only term for this one. Similarly, phi of 2 comma 0 according to this is a of 1 into a of 0. So, from here when we put k equal to 0 and 1, we will get these two matrices as the state transition matrix part of that. Then M is calculated by this expression, and by substituting the appropriate matrices we get the M to be non-singular because the determinant is non-zero. So, the system is observable. Now, let us consider the following. The state transition matrix is given by phi of k k 0 is a k minus 1 etc. a k 0 according to the definition. Then the transpose, or when we write phi of k 0 k, in the previous lecture we have seen the definition of phi of k 0 k is the inverse of phi of k0. So, it is given by A inverse k0, A inverse k0 plus 1 etc. A inverse k minus 1, the inverse of the previous step. So, and if we take the transpose of this, we get A inverse k minus 1 and its transpose, then A inverse k minus 2 transpose etc., A inverse k 0 transpose. So, this we denote it by xi of k 0. The notation for the right hand side of 9 is denoted by xi of k 0. So, now let us consider the two systems, x of k plus 1 equal to A of k x of k is one system, and another is y of k plus 1 is A inverse of k transpose into y of k. K is ranging from k0 plus 1 etc., and maybe the last is k0 plus n. So, we see that the state transition matrix of equation 11 is given by equation 8 here because of the matrix A. Similarly, the state transition matrix of equation 12, because of this matrix, the first term should start with k minus A inverse k minus 1 transpose and etc. The last term should be A inverse into A inverse of k0 transpose. So, the xi k0 is the state transition matrix of state transition matrix of the equation 12 here. Okay. And from this equation we can easily see that xi of k0 is nothing but phi of k0 k transpose, that is seen from equation 9 and 10. So, we can see that the relation between the state transition matrix of 11 and 12 are given by this expression, psi of k0 is phi of k0 k transpose. So, this we can utilize in the following way. Now, let us consider the two systems, x of k plus 1 is A of k x of k plus B of k into u of k, and the observation y of k is c k x k, that is the usual system which we have considered earlier. Now, we will consider another system, x bar of k plus 1 is equal to A inverse k transpose into x bar of k plus c bar of k into v of k, and the observation for this system is y bar of k equal to b bar of k into x bar of k. So, here this x and x bar directly they do not have any relation. So, it is simply a notation for a different system, and similarly this y and y bar they do not have direct relation, but these are two different systems observations. Y is observation of system 14 and y bar is observation of system 15. Now, let us select this c bar to be equal to c dashed of, in the equation 15 we select the matrix c bar as c bar of k is equal to c dashed k plus 1 and b bar of k is b dashed of k minus 1, because we know the matrices A, B and C. So, in terms of A, B, C we are writing the matrices this B bar, C bar etc. So, now we can easily verify that the controllability condition of system 14 is same as the observability condition for equation 15. because we can see that the controllability of equation 14 so that implies and implied by the matrix summation I is equal to k 0 to k 0 plus n minus 1 of phi of k 0 I plus 1 b of I into b dashed of I into phi of k 0 I plus 1 phi dashed. So, this expression it is non-singular. This is called the controllability Gramian matrix, and if this matrix is non-singular, the system is controllable, and if the system is controllable, this is non-singular. So, we have seen it in the previous lecture. So, this condition is same as, so now this implies that this is equal to summation I is equal to k 0 to k 0 plus n minus 1, and this gives xi of I plus 1 k 0 dashed. So, earlier we have seen that phi and xi have the relation like this, phi xi of AB is phi dashed of BA. So, we get this relation, and B of I. So, according to this one, we have B dashed of I is B bar of I plus 1. So, we get here B of I is nothing but B bar dashed of I plus 1, and B dashed of I is B bar of I plus 1, and phi dashed k naught I plus 1, that is nothing but xi of I plus 1 comma k naught. So, this expression we can easily see that this is nothing but the observability of the equation 15, isn't it? By seeing the observability Gramian matrix, we can see that it is the same. So, we get the result, the controllability of 14 implies observability of 15. Similarly, observability of 14 implies the controllability of 15, and vice versa, both sides. So, these two systems are called the dual systems, the 14 and 15 are called the dual system, and this result is called the duality theorem. Okay, this one is so this is similar to the case of the continuous time systems. So, in the continuous case, we have seen that if we take x dot equal to Ax plus Bu and y of t equal to C of t into x of t, this is the control system and the observation. Then the system x bar dot equal to minus A transpose x bar plus C dashed of some control V, and y bar of t equal to B transpose of t into x bar of t. So, the first system and second system are dual to each other. The controllability of this equation 1 implies the observability of this equation 2, etc., vice versa. So, this duality theorem is similar to the duality theorem for the discrete system here, and so using this we can derive similar conditions as in the case of the continuous systems. So, using this result we can also observe that the observability of the autonomous system, autonomous discrete system, if A, B, C all of them are constant matrices. So, we can conclude that the rank of C, C A, C square A, C sorry okay. So, the condition, the rank C, C A, C A square, C A n minus 1, if it is equal to n, then the system is observable, or if the system is observable then the rank of this matrix has to be n. So, this can be proved using the duality theorem for the discrete system. So, because we know that the controllability of the equation 15 is given by the rank of B A B A power n minus 1 b equal to n, when A B are constant matrix, this is the condition. So, using the controllability and observability relation of the dual system, we can prove that the observability of equation 4 will give the condition for the controllability of equation 15, and similarly the controllability of equation 15 will give the observability condition for the equation 14. So, that will turn out to be this condition. So, with this we close the lecture on the observability and the relation between observability and controllability of the dual systems. So, thank you.